That's Thanksgiving week, just one day today, just one class period, yay. And then after today, then we have 6 more class periods after Thanksgiving, starting next Monday. It's not going to be a piece of cake though, it's going to be tough material, chapter 8, rivals chapter 5 for the toughest material. The proofs perhaps that you need to be responsible for are perhaps not as hard, but it's more abstract, and so maybe some people would think of them as being harder than chapter 5 was on integrals. There's lots of definitions to learn too. So get yourself psyched up, pray, ask God for strength to work hard. You will need to work hard these last few weeks leading up to the final exam. I think for the closed book portion of the final exam, closed notes, closed book, and there will be an open notes portion as well. So we'll just focus on definitions and theorem statements from chapter 8. So that part won't be cumulative. But the open notes portion, which you probably shouldn't be paging through all your notes, you probably should just have it on like one piece of paper just to keep things centralized. That'll be more cumulative.
So is the open note going to be more computational sort of stuff?
Computations and proofs, yeah. And being proofs, probably they won't be something from the book because I will let you use your book. You can have your book with you, you can have a piece of paper and a calculator, write stuff on the piece of paper. I would recommend doing that. I still need to do your journal check, so you really want people to look in your journal. But having those things there will hopefully reduce the anxiety. But I probably won't be giving you proofs that are in the book, since you'll have that there. Don't think we'll need Mathematica much today, if at all, so I'll have it up just in case. So today we're going to talk about what you could call topology of the real line, focused on the real numbers as a topological space. Next week when we come back, we're going to generalize things a bit. You're only going to have your study guide through section 8.3, and as of the moment at least, only completion problems through 8.3, but I'm going to cover section 8.5 in class, skipping perhaps 8.4 to a large degree at least. And there won't be any study guide to do for section 8.5, but there may be some completion problems yet to do. I'm going to decide based on what we're able to do. I do want to talk about this in the context of some applications as well. We're not going to see any applications today. But next week and then the last week of class, I do want to look at some applications. The applications will involve sequences generated by iterating functions and studying those sequences and trying to understand their behavior. All right, so let's start with, I'll describe this as an important property of open intervals. I do want to still talk a little bit about chapter 7 as well, a little bit more about Taylor series, but not today. Probably next Monday or next Wednesday. Important property of open intervals, what is this? Well, first of all, let's let A and B be in R with A less than B. Given any number x in the open interval from A to B, you can prove, and I will prove, and you should be able to prove this. There exists a positive number, let's call it R, what calls it typically, such that the open interval of radius r centered at x is a subset of the open interval from A to B. There's an important property of open intervals that's not shared by closed intervals. It's important to be able to visualize this, what's going on here, and also see why it doesn't work for closed intervals, or half open, half closed intervals for that matter. So we've got an open interval here from A to B, so we're not including A and B in the interval. There's our set that we're considering here. Of course, I'm drawing these circles large, but it's really just single points that are missing. The endpoints are not part of the set. Give me any point x in this interval, it doesn't matter where. Could be here, could be there, could be really, really close to B but not equal to B. There's some positive number, perhaps really small, so that this interval of radius r centered at x is inside the given open interval. Okay, so if x was really close to B here, but not equal to B, then r would have to be really small. You could pick r to be half the distance between B and that point, and you get a little open interval centered at x of radius r that's still inside the given open interval. You got a closed interval, or a half open, half closed interval. If we include A as part of the set, this is no longer true, because if x is A, then no matter how small r is, an interval centered at x will include points to the left of A and will not be a subset. Or, well, okay, if we included A in the set, then we use a square bracket there. So this is true about open intervals, not closed intervals, not half open, half closed intervals. Let's prove it. And this is a proof you should be able to do. So you're given the x. The picture gives you a hint as to how to pick r. Given x in the open interval from A to B, let r equal, well, you don't know if x is where x is. X is arbitrary. Is it close to B? Is it close to A? Is it halfway in between? You don't know where it is. How can you have an idea how you can take care of the fact that you don't know exactly where x is? I sort of said if x is real close to B, you could let r be half the distance between B and x. But what if it was really close to A? Any idea how we can deal with the fact that we don't know where x is? Take the minimum, yeah. And if you want to play it safe, well, maybe we could do b minus x over 2 and x minus a over 2. That would work. Actually, it's good enough to just do b minus x and x minus a. That would be good enough. This is positive. This is an open interval. X is in that open interval. It doesn't equal a or b, because A and B are not part of the interval. This is a positive number. That's important to note. If I gave you this proof on the final exam, you wouldn't get full credit unless you make note of that fact. R is positive here. Again, it's also because B is bigger than X and X is also bigger than A. That's clear. You don't need to say that, but you should emphasize that this is positive. We claim that this works. The interval from x minus r to x plus r is a subset of the original interval. Before I prove that claim, which finishes the proof, let me make another note over here. So we let r equal this. Therefore, r is bigger than or equal to b minus x, and r is bigger than or equal to x minus a. That'll be important to note. If r is the min of b minus x and x minus a, then it's bigger than or equal to both of them. How do you prove such a claim? We're going to do a lot of this kind of proof in Chapter 8. You want to prove one thing is a subset of the other. This goes back to the preliminaries handout. You got to give me an arbitrary thing in the first set. I got to show it's an element of the second set. That's how you show this set as a subset of that. You can look back in the preliminaries handout to see that. So to prove the claim, let y be in here and show y is in there. Let y be an element of this interval, show it's an element of this interval. In other words, the fact that y is strictly between x minus r and x plus r should be enough to show y is strictly between a and b. And this has got to be relevant. How so? Or should we might have been good to put that up here, but let's go ahead and put it down here. Since r is bigger than or equal to b minus x, it follows that what? It follows that, which way do I want to do it here? I want to show x plus r is less than b, less than or equal to b. Looks like I have it greater than or equal to. Where's my mistake? So I did this ahead of time. So I was thinking I didn't make a mistake.
I don't understand why if it's the min of b minus x and x minus a,
Ah,
and
that's
it's
my
greater than
mistake.
equal to both of them.
Thank you.
Okay.
I got mixed up. It's less than or equal to both. Thanks. But I caught my mistake. I was realizing this wasn't working. X plus r will be less than or equal to b. Since r is less than or equal to x minus a, I want to relate it to this thing. I hope that's bigger than a, greater than or equal to a. Subtract r from both sides and add a to both sides. A will be less than or equal to x minus r. That does it. Y is between x minus r and x plus r. X plus r is less than or equal to b. R is less than or equal to x minus a. Or excuse me, a is less than or equal to x minus r. Therefore, a is less than or equal to x minus r, is less than y, is less than x plus r, is less than or equal to b. That shows that y is strictly between a and b. So y is in the open interval from a to b. And we're done. That proves the claim, which proves what we wanted to prove. Question?
Why does r have to be greater than 0? What if a was like -5 and b was -5?
Well, the r being greater than 0 is what we're trying to show. We're trying to show there exists an r, where that's true. This is positive because I'm assuming x is strictly between a and b. That means b minus x is positive and x minus a is positive. Since x is between them, I'm assuming that. R being positive is part of what I'm trying to show. There exists a positive R like this. Okay? This property of open intervals is fundamental to open intervals. It's going to be the main fundamental thing that we use in Chapter 8 about open intervals, actually. It can be extended to unions of open intervals, too. An important property of unions of open intervals. So, how should I describe that? I should say suppose I've got a collection of open intervals. What kind of collection is this? Could be a finite collection of open intervals. Could be an infinite collection of open intervals. I could have infinitely many open intervals that I'm taking the union of. That infinity, the cardinality of the infinity could be countable, same as the cardinality of the natural numbers, or it could be uncountable, bigger than the cardinality of the naturals. I'm saying I could be taking the union of an arbitrary collection of open intervals, which could be an uncountable collection, theoretically. It's a collection of open intervals. I'm going to label the endpoints of those intervals A sub alpha and B sub alpha. Alpha is going to be like my index for this collection. Alpha could be an integer, 1, 2, 3, 4, 5, 6, etc. Or it just could be an element from some set, some unspecified set. It's often traditional to use a capital omega as your unspecified set here, kind of strange. Or with alpha and omega beginning and end there.
A little wrap.
Yeah. Omega could be the natural numbers. And so alpha could be a positive integer. It could be some other countably infinite set like the rationals. Could be uncountable like the reals or some other uncountable set. I'm not specifying what it is. It can be anything. So we got a collection of open intervals. If X is in the union of those open intervals, as alpha varies over omega, then there exists a positive R such that the open interval centered at X of radius R is a subset of that union. So unions, the point here is unions have the same property that open intervals do. Given a point in the union here, there's some little tiny open interval centered at that point, conceivably tiny, it doesn't have to be tiny, that's in the union. This is pretty easy to prove actually once you've got the other fact that I erased. What does it mean to be in a union like this? A point is in a union of sets if it's in at least one of the sets. To be in an intersection, you got to be in all the sets. For a point to be in the union of a bunch of sets, you just have to be in one of the sets, because you're combining all the sets to form the union. You can say there exists an alpha sub 0, say, such that X is in the open interval from alpha sub 0 to beta sub 0. Oops, sorry. A sub alpha sub 0 to B sub alpha sub 0. That's what it means to be in the union. That's basically the definition of a union. But that's an open interval. Therefore, there exists a positive R such that the interval from x minus r to x plus r is inside that one open interval. But that means it's also got to be a subset of the union. Done. I guess I'm saying it's a subset of the union without proof. The proof is very easy. It is basically clear. Well, maybe I should briefly say it verbally. I would accept stepping from there to there as an obvious thing. I guess it's just as obvious as going from here to here, and I said that, but give me a point in here. I got to show it's in there to show this is a subset of that. If it's in there, if y is in there, then it's, by this fact, it's in there. But that's one of the sets you are unioning. This is definitely a subset of the union. The only thing that makes this difficult is its abstraction, okay? The abstraction just takes some getting used to think about abstract concepts clearly. Once you get used to that abstraction, this is a relatively easy proof, okay? Kind of like in algebraic structures, things seem really hard at first, and they continue to be hard. I'm not saying they didn't, they got easy, but the earlier stuff in algebraic structures, when you first learn about groups, you learn about closure and associativity and existence of inverses and so forth, identity. That seems really hard at first, but when you get into the extra complicated stuff, you go back to the beginning and you're like, oh, that was easy. Didn't you feel that way? Going back and looking at the initial stuff compared to things like factor groups and normal subgroups, right? The earlier stuff is relatively easy. It doesn't feel that way at first. Same kind of thing here. It doesn't feel easy at first, perhaps, because it's abstract. But it's easier than what comes later. Okay. So these are exam possibility proofs on the exam. You know, exam proofs either need to be easy or only moderately difficult with maybe a few hints here or there. They can't typically be very hard. So this is something you should be able to do. Go back and change this yet again. An important property, what about intersections? I do union, should I do intersections? Well, you got to modify things a little bit. The intersection of finitely many open intervals. This property will not, in general, be shared by the intersection of infinitely many open intervals. So now we have a finite collection of open intervals. So let me go ahead and use a more natural index here, I, where I goes from 1 to n, where n is a fixed positive integer. That's be a collection, a finite collection, for extra emphasis, finite collection of open intervals. If x is in their intersection, which you can write with just one intersection symbol, like we wrote one union symbol before, like this. Or you could write out A1, B1 intersect A2, B2 intersect dot 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 intersect AN, BN. Either way of writing the intersection of finitely many intervals is fine. Then there exists an R, a positive R, such that this set is a subset of this intersection. Let's prove this, and hopefully in the proof we'll see why it wouldn't work for infinitely many. So let x be an element of the intersection. What does it mean to be in an intersection of sets? It means you're in all of the sets. The intersection is what the sets have in common. So if a point is in an intersection, it's got to be in all the sets. So it's not that there exists something so that this is true. It's for all. The quantifier changes. For all I equals 1 through n, x is in the open interval from ai to bi. If it's helpful, you can draw pictures here at least. We are still dealing with the real number line. We're taking an intersection of open intervals. Very well could be the empty set, actually. Which means I probably should modify how I say this. Well, okay. Actually, saying it this way is still okay. I'm saying if x is a point in here, then this will be true. It's possible this could be the empty set, which means this hypothesis might not be true in that case, which makes the if-then statement still true, right? Vacuously true, they say. If the premise hypothesis is false, then the if-then statement is actually true no matter what. Right? Learn about that in discrete math. This if-then statement is still true as an implication, even if this intersection is empty. And you can't have a point in the empty set. It becomes a vacuously true statement is the way people phrase it. So I don't need to modify it and say assume this is non-empty. By writing x is in there, I'm implicitly assuming it's non-empty. That's part of the proof. So maybe A2 and B2 are here and here. A3 and B3, etc. Well, maybe I only have 3 sets. Their intersection would be this thing. In this picture, your point would be in all of them. And for each one of them, each one of these is an open interval, you're going to have an R for each one of those. Call it R sub I, since there's one R for each one of them. Therefore, there exists positive numbers R sub I going from 1 to n positive numbers, such that the open interval centered at x of radius R sub I is a subset of the open interval from ai to bi. We've got finitely many r's. In the conclusion, I want just one r. What do you think? How should I define my one r? Use the min again, yeah. Let r be equal to the min of r1, r2, r3, etc. Let me get the direction of the resulting inequality right this time. So that, okay, r is the smallest of these. It's less than or equal to all of them. R is less than or equal to Ri for all I. Right, it's the min, it will be less than or equal to all of them. And there are finitely many of them, and they're all positive. The min has got to be a positive number. That's important to emphasize. It's not like we're taking an inf of an infinite collection of positive numbers. The inf could be 0. The inf of an infinite collection of positive numbers could be 0, even if all the numbers that you're taking the inf of were positive. I could call this an inf here, it wouldn't matter. Inf and min are the same when you've got finitely many numbers. Since there are finitely many positive numbers here, that min, that inf, would have to be positive. That's important. And that's the place where the if you were doing an infinite intersection, that's the place where your proof would break down. If you let R be the inf of an infinite collection of Ri's, that's not necessarily positive. That's where the proof in the infinite case would break down. It's also important to realize that you can come up with examples of infinite collections of open intervals whose intersection does not satisfy this property. For example, if AI BI was the interval from -1/I to +1/I, where I goes from 1 to infinity, the intersection of this collection would be a 1-point set 0, which definitely does not satisfy this kind of property. So the proof does break down, and you can also, more importantly, come up with examples to illustrate the property breaks down if you've got an infinite collection of open intervals that you're taking the intersection of. The claim, the open interval from x minus r to x plus r is a subset of the intersection here. That's perhaps a little less obvious. This is worth proving. Let y be in the open interval from x minus x to r to x plus r, so y is between x minus r and x plus r strictly. But each r is less, well, r is less than or equal to each ri. And each of those intervals is a subset of the corresponding original open interval. Therefore, for all I from 1 to n, you can say AI is less than x minus Ri is less than or equal to x minus R. R is less than or equal to Ri. So negative Ri is less than or equal to negative R. This inequality is correct. I'm subtracting something bigger, so to speak, here. It's got to give me something smaller than that. For all I, this is true. Therefore, y is in this intersection as well. Okay, we're done. That's definitely a bit trickier of a claim, or it's definitely worth showing the details. Okay, this leads us to the definition of something called an open set. Open sets in general satisfy the property that I proved each of these three things satisfy in each of these three claims that I made in three proofs. That's the definition. The book uses the letter capital E a lot in chapter 8 to denote an arbitrary set, subset of the real number line, and I will use that sometimes. They also use the capital letter O to denote open sets. I will go ahead and use an O to denote an open set here. However, if you make it look like the book's O, it looks like a 0. So I'm going to make mine recursive. Like that. That's an O, a recursive O. O for open. Okay, a set O in R is open are in parentheses because we'll see later that sometimes it will be necessary to specify something as open in something else. It would be okay if you didn't put that here though, because it's assumed the underlying space is the real number line. If for all x in O, there exists a positive R such that the open interval of radius R centered at x is a subset of O. That's the exact same property I proved first for open intervals, then for arbitrary unions of arbitrary collections of open intervals, and finite intersections of open intervals. In other words, the intersection of a collection of finite many open intervals. The same property. Now we're saying this is a definition. It turns out it can also be proved, though I'm not going to prove it today, if at all. Maybe I will prove it at some point. That any open set, any open subset of the real number line is a union of open intervals. In fact, it's even better than that, though the proof of what I'm about to say is harder. If you happen to have your book, you can look at page 296. I should say every non-empty open set. What I just said was, if I add non-empty, is this. Every non-empty open set is the union of open intervals. That can be proved, and the proof is actually fairly easy, relatively speaking. It's still abstract. It's a bit harder to prove the theorem on page 296. It says something a little bit stronger. Every non-empty open set of real numbers can be expressed as a countable union of disjoint open intervals. That's a bit harder to prove. And you can see the proof. It takes up about half a page, and when you glance through it, it doesn't look too easy. Not super hard, but it's not super easy either. Soups and imps become involved, for one thing. So that's a bit stronger theorem. You can get a countable collection of open intervals. To show it's a union of some collection of open intervals is actually pretty easy proof. Maybe I'll do that on Monday. So every open set is a union of open intervals. And of course, by what I said just 10 minutes ago, it works the other way too. Every union of any collection of open sets is open. What I'm about to do for the time we have remaining today is I'm going to jump forward to section 8.3. What we've been doing so far is essentially part of 8.1, only a chunk of 8.1. You should read all of 8.1, which has got a lot of other ideas in it, including the idea of a closed set. There's open sets, there must be closed sets. Yeah, there are. In fact, they're complements of each other. There are plenty of sets that are neither open nor closed, though. The complement of any open set in the real number line is a closed set, and vice versa. But there are plenty of sets that are neither open nor closed. What I want to do for the remaining time is jump ahead to section 8.3, essentially, and relate the ideas that we've been talking about so far to continuity of functions. Write down a theorem. For sake of simplicity, I'm going to assume that I've got a function whose domain is the entire real number line and whose codomain can be considered to be the entire real number line. This theorem can be generalized to domains that are smaller than the entire real number line. But to keep things simple today, like that way. then F is continuous on all of R, not just at a single point, not at a couple points, not at some subinterval, some proper subinterval, all of R, if and only if you can state the conclusion, the other part after the if and only if in a couple different ways. Here's the way I'm going to say it. For every open interval, I think I'm going to call the open interval the endpoints C and D this time, because it's going to be a subset of the codomain. It's going to be thought of that way. For every open interval from C to D, remember this notation? F inverse CD, what? It's not the inverse function of F. What did I call this notation? Does anybody remember back in chapter 3, I think? We talked about this notation. It's got two names, actually. Sometimes it's called the inverse image. Sometimes it's called the preimage of this set. If and only if this preimage is open in R. What is this thing again here? Again, it's sometimes called the inverse image of the interval from C to D under F. I think a better term is preimage. Inverse image makes you think there's an inverse function for F, but not necessarily. So I think a better term is preimage. Preimage of the interval from C to D under F. I will sometimes say either term, but I think preimage is a better term to use. Okay, I use the word inverse image. Don't make that think that that means F has an inverse function. F might not be one-to-one. So it may not have an inverse function. What is the set? In general, if you've got a function whose domain is A and whose codomain is B, and you've got a set that's a subset of the codomain, the preimage of that set under the function is the set of all points in the domain that get mapped into the given set in the codomain. This is A, and this is B, and C is some subset of B. The preimage of C under F is some subset of A. It's all the points in A that get mapped into C. So this is all the points that get mapped into the interval from C to D. So what I'm saying here is the idea of an open set is fundamental to really understanding continuity on sort of a global scale over the entire real number line here. This is definitely not obvious if this is true. I would like to sketch the proof in the time we ever made. It's a hard proof. Would it be an exam level proof? Well, I'm not sure. If it wasn't the exam, it'd probably be just one direction since this is if and only if. And I might have to give you some hints if I did put it on the test. What do we have? Try to finish in 10 to 15 minutes here. Sketch it proof. Make things go faster. I'm going to avoid writing sentences here. It's if and only if. What would the forward direction look like? I'd have to prove that if F is continuous on R, then this condition here is true. Go back to the definition that I just erased of what an open set is. I'd have to show that if you give me a point in here, call it x, that there's some positive r, so that the open interval centered at x of radius r would be a subset of this. That would do it. Give me an x in this preimage. When I talked about preimages before, I also mentioned that they came up in algebraic structures. A preimage of a subgroup of a group is a subgroup of the domain group, or homomorphism, under a homomorphism, I should say. Give me something in there. I have to find an r, positive r, so that the interval from x minus r to x plus r is a subset of this. How in the world are you going to do that? Well, it's sort of a follow your nose kind of thing. What's the only logical next step? What does it mean to be in this preimage? It means that f of x is between c and d. Maybe I'll just do a bunch of implications here. That's what it means to be in that preimage. X is in this preimage. That means it gets mapped under f into this set right here. F of x must be an element of that. Well, what does that mean? Well, the interval from c to d here, that's an open interval. We know it has the property that there's some r, some positive r, where the interval of radius r centered at f of x is going to be a subset of this. Instead of calling it r, let's call it epsilon.
Definitely a follow your nose kind of thing.
Well, no, we want to show it's continuous. Epsilon was the letter we used for limits, so it's a natural thing if you think about it. There exists a positive epsilon such that the open interval of radius epsilon centered at f of x is a subset of the interval from c to d, because c to d here is an open interval. Draw a picture if it's helpful. Yeah, f of x doesn't have to be 1-to-1. C might be here, D might be here. What does the preimage look like in this picture? Actually, let me make C and D closer to make it more interesting. What's the preimage of this open interval here under this function? Part of it would include these points there, but part of it would also include these points here and these points down here. Those points in those three intervals, those three open intervals, would get mapped into this open interval under F in this picture. The union of these three open intervals is the preimage. For this picture, for this interval. If x is in the preimage, it's in one of these three intervals. I don't know which one. Doesn't really matter. F of x is going to be between c and d. There's some epsilon so that the interval from f of x minus epsilon to f of x plus epsilon is a subinterval of the interval from c to d. F is continuous on R, so it's also continuous at x. Therefore, there must exist a delta. F continuous on R means F is continuous at x, which means there exists a delta, or maybe I should call it R. Doesn't matter what you call it. Exists a positive R such that what? Continuity. If the distance between x and y is less than r, which is like my delta, this implies that the distance between f of x and f of y is less than epsilon. That's chapter 3. Definition of continuity. Using an r instead of a delta. It would be okay if you used a delta. I wonder if this r is the r that works. Shall I go ahead and claim it works without proof? Well, okay, if you do claim it works without proof, you've got to prove that claim. I could call it claim, or maybe I could just say hope. Hope. I'll write claim. Claim the open interval from x minus r to x plus r is a subset of the preimage. If that's true, we're done with this direction of the proof. Right? Because I'm trying to show that preimage is open. I'm trying to show that's an open set. So it's got to satisfy that property in the definition that I erased. Is this true? I'm not going to prove it completely, but let's see if we can just verbally, in our minds or imaginations, I should say, believe it. To show this is a subset of that, you got to show, say, give me an arbitrary point in here, and show it's in there. Let y be in there. What does that mean? It means the distance between x and y is less than r. It means this is true. Which then means this is true. Which then means f of y is within epsilon of f of x. It's in there. F of y is in there, which means it's in there. Done. Should I do that again? You can watch it on the video if your heart's still late, over and over again, until it becomes clear. I want to show this is a subset of that. I got to say, give me an arbitrary point in here, show it's in there. Let y be in here. Then y is within r of x. So this is true. Which means this is true. Which means f of y is within epsilon of f of x, which means f of y is in here. Which, by this fact, means f of y is in there. Which means y is in this preimage. I should have said that at the end. How about the other direction of the proof? Out of time. So I'd have to say if I have an open set, if for every open interval C to D, this preimage is open, that implies f is continuous on R. I'd have to start by saying let x be given. To show f is continuous on R, it's enough to show it's continuous at an arbitrary point. And then I'd say let epsilon be given. And I'd have to find a delta, or an r, you might prefer, so that if this is true, then this is true. Let me just say, to finish off, that it's this condition here, we're going to assume is true. The preimage that you consider is the preimage. We'll use the fact that the preimage of the interval from f of x minus epsilon to f of x plus epsilon is going to be open. You'd use that fact. Find an r or a delta positive to make this fact imply this fact. You'd use the fact that this is open. And that would be using the other condition here. This is something that takes time for it to sink in, as most math does, but this is probably more than most math. You gotta work pretty hard here to get this. Okay? See you in 1 week.